Good evening, everyone. I'm Narayanan Sundaram, and I work at Intel Labs. And my talk today is going to be about GraphMat, about bridging the productivity performance gap in graph analytics. So this is a project in Intel Labs. It's not a full-fledged product. So this is our effort towards trying to make graph analytics be more efficient and faster while still trying to maintain the productivity benefits. So how many of you here have tried to work with graphs, use any of the graph frameworks, Giraffe, GraphX, GraphLab, something? Okay, so at least about 20% of the group has some experience with graphs. So I don't want to motivate too much on the fact that graphs are important. I think at least a sizable fraction of you know that graphs are important, at least, even if you haven't worked with it. You've heard enough speakers talk about graphs. But what I do want to impress today is that a graph performance needs to be faster and better. So what we do want is to have frameworks that improve the current performance by at least an order of magnitude or more. So to begin with, an example from Intel Security. So this is a cybersecurity application. What we were trying to do there was run loopy belief propagation for doing device reputation management. So you have a device graph and URLs, and there's communication between all of them, and some of the links are tainted, some of the devices have malware, and you're trying to get reputation scores for all of them. And this is a fairly large graph, a few billion vertices and edges, and this is something that we wanted to update every day because the reputation scores keeps changing quite frequently. And when we coded it on Giraffe, this took us almost a day to run with 16 machines. And as you can see, this was actually with less than a week's worth of data, this graph. What we really want to do is collect data for several weeks and then run device management scores, and that is clearly out of scope for this unless we increase the hardware budget tremendously. Not just that, if we move from the current state of the art to Internet of Things, the number of devices explodes exponentially. So how do you do reputation management in that area without increased performance? It's clearly impossible. Not just cybersecurity, but in social networks as well. Facebook recently published this paper where they claimed that they were able to run PageRank on a trillion edge graph on 200 machines using Giraffe, roughly taking 3 minutes per iteration. So assume that your PageRank converges in, say, 20 iterations. You're still going to occupy 200 machines for an hour to just run PageRank. And this is something that this is a global property over the entire graph. What if you want to run something that's more personalized? What if you want to run a global algorithm, but tailored to specific individuals, like personalized PageRank? You can't even do that for the top 1% users without increasing the performance. What we've seen is most of the graph analytics frameworks, not just Giraffe, but pretty much all of them are severely handicapped by their performance. So we have actually tried to fix that problem. And if you look at the problem scale, not just a couple of social networks, of course, they are the first to be here. You have order of billion vertices and 100 billion connections. This is just to give you an idea of the scale. And web graphs, which are about an order of magnitude larger than social networks, up to a trillion hyperlinks or so. And brain, natural neural networks of the order of 100 billion neurons and 100 trillion connections. So if these are really large graphs, we do want to do complex analytics on all of these. So let me introduce GraphMat. What is GraphMat? GraphMat is our graph programming framework, uses Vertex programming as its front end, but in the back end, uses sparse matrix vector operations. So what we really have tried to achieve here is give the user all the flexibility of Vertex programming. If you're familiar with GraphLab or Giraffe or Pregel, you probably already know how to do Vertex programming. The idea is to think like a vertex. So every vertex can communicate with its neighbors, send messages along its edges, and you can receive messages, process those messages, and then update your state. So these are the primitives there. I'll go into a little bit more detail in a few slides, but the idea is that this is pretty easy to reason about and write a lot of programs. So what we try to do is maintain the Vertex programming abstraction so users do not have to change the way they are thinking, but at the same time, we've replaced the backend of a graph programming framework with completely replace it with generalized sparse matrix vector multiplication and sparse matrix multiplication operations. So how can it help you? If you're one of those people who feels that you have large-scale graph problems to do, you know Vertex programming and you like it, but Giraffe or GraphX or Pregel or GraphLab is too slow, I want something faster. Or if you're someone who's heard about how graph programs can be written as matrix operations, this is not entirely new. People have been writing books about it. But then you want the performance of matrix programs, but you really do not want to recode all of your Vertex programs to use matrix algorithms. So if you fall into any of these scams, or are you just curious about how fast any of your graph algorithms can run, you can definitely take GraphMat and try it out. So this is an open source project and licensed under BSD, so you can download it and try it out. So why are we doing this? Why GraphMat? So what we want to do at Intel Labs is to enable super fast but distributed graph processing on x86 servers. So this is the mission statement here. And why do we want to do this open source? Because we want to enable this for everybody. So if you have any framework, any distributed machine learning framework that you'd like to use, and you'd like to have fast graph processing in there, you can take GraphMat and integrate it with it. It's written in C++ with MPI. We're constantly trying to making changes to it. If you have any suggestions, you can definitely let me know, and it's released under BSD. You can integrate it with your frameworks. If you have, we can definitely help you, so just contact one of us. So GraphMat is the current state of the art. It's actually faster than pretty much all the other distributed graph frameworks that we have tested it over. Things like GraphLab, CombLast, GraphX, Giraffe, and many others. It's optimized for both multi-node as well as multi-core, uses Vertex programming, so the user doesn't have to change the way they are thinking. And we are, what we are bringing new to the table is bringing all the optimizations that people in the high-performance computing and supercomputing world have studied about sparse matrix operations over decades. So papers have been written, several PhD theses have been written on how to optimize sparse matrix operations on clusters. And we at Parallel Computing Lab have a lot of experience in high-performance computing. And what we want to do is bring all of that expertise over to the big data, big graph processing world. And that's what we've tried to do with this project. So if you look at the current graph frameworks, you have a huge variety. You have a huge bunch of frameworks that expect you to program in Vertex programming, as in think like a Vertex. Things like GraphLab, Giraffe, MapGraph, Pregel, GraphX, and many more let you do this. And then there are other frameworks which expect you to write matrix operations. Frameworks like CombLast or Pegasus. Basically, you can only write matrix vector multiplications and generalized matrix multiplications, and you basically have to twist your graph program into a matrix operation. Or you have other frameworks like Galois, which expect you to write a task graph, and they take over, and their runtime can execute it efficiently. You have other programming frameworks like Socialite, which expect you to write data log, or you have domain-specific languages like Greenmal, which basically say that, oh, graphs are so specialized that we are going to give you a new language. And not just in terms of programming diversity, there is also a huge diversity in terms of performance. So this is just several frameworks running PageRank on a relatively small graph. And you can see that compared to where Giraffe was, a native hand-optimized C code, making sure we wrote all the software prefetches and everything to like really peak out the hardware performance, is about 2 orders of magnitude off in performance. So you can actually get much higher speed-ups if you're willing to actually hand-code your application. That's clear, but the gap is actually 2 orders of magnitude. And what we really want to do is stay in Giraffe or GraphLab, have the same productivity, but get performance that's closer to native code. And continue, so this is from our studies, we basically felt most of the Vertex programming frameworks like GraphLab, Giraffe, GraphX have good productivity. It's easy to reason and write programs, but their performance is not all that great. Things like Galois or CombLast, it's relatively hard to write programs, but once you do, they actually run well and they scale well. And GraphMat, we've tried to bridge both high productivity as well as good performance. So what are we basically assuming in this project? One is Vertex programming is productive. It's actually easy. If you feel Vertex programming is a really terrible way to do graphs, then please, you can talk to me. I'll try to convince you why this is good. Fewer building blocks are better. We are building everything on top of sparse matrix operations. These are well-studied, well-known, and you have relatively few things to optimize, even on distributed processors. You don't have complicated schedulers. You don't have complicated task graphs to deal with. Everything becomes simplified. And sparse matrix operations are scalable because we know from the high-performance computing world, we've done all the work over several decades to make sure that things are scalable. And very few people have the ability or the interest to code to the metal. So once a framework like GraphMat exists, it will be very easy for all the other Vertex programming frameworks to adopt it. Just use it as a backend. Even if you do not want to use GraphMat itself, you can take all of the ideas from using matrix operations, and you can port it over to your own framework of choice. And right now, we are assuming that you can use MPI, which is message passing interface, in a distributed setting, even on a cloud. This assumption may be relaxed in the future because we have heard complaints that MPI is not going to work all that well on the cloud, so we are looking at alternatives. But right now, we have everything working on MPI in a distributed setting. And the other assumption that we have is that the graph data fits in memory, which means it is an in-memory framework. It's not working out of core. So at a very high level, what we have is how to move from the Vertex program on the left to our transformations on the right. So what we have on the left is pretty traditional Vertex programming. So you have these user-defined functions that change with every different graph algorithm. So you have a function that says how to send message to its edges, how to process an incoming message, and how do you collect or reduce the results of several incoming messages, and how do you use that to update your Vertex state. And this is what the user sees, and this is what the user programs. On the right, what we really do is take each of these steps and convert it into a corresponding matrix operation. The send message becomes a create sparse vector, process message and reduce become part of a generalized sparse matrix vector multiplication, and apply is basically a data parallel operator operating on sparse vectors. And if you are familiar with the scatter gather apply model, send message is typically the scatter phase where you scatter messages along all of your edges. Your gather is basically collecting your incoming messages and processing them. So that is what takes most of the time in all of these graph programming frameworks, and that's what basically becomes a generalized sparse matrix vector multiplication. And the apply phase is just basically whatever you operate on your Vertex. And the benefits are, again, the users still have to do only Vertex programming, but you get high performance because the backend is pretty well optimized. So to give you a quick code example, so this is in C++. So we do have C++ template specialization for handling arbitrary data types. So you're not restricted to the few data types that we provide. You can write whatever you want. You can process in edges, out edges, all edges, and you have a few more customization options. And then you basically write your 4 functions that define your Vertex program. So this is all you basically have to write. So this is for calculating Vertex degree, looking at all the edges. If you want to look at only in degree or out degree, that's just a very simple change. Almost all of our programs just follow this template. What is new? Graph algorithms as linear algebra are pretty well known. Books have been written about it, the famous one by Jeremy Kepner as well. What is new here is unifying Vertex programming with linear algebra. So you can write your graph programs as Vertex program without even thinking of matrices and having everything else taken care of for you automatically. So I will run through a quick example. So we have a graph on the left, which is 5 vertices and several edges. And on the right, we have I have shown the transpose of the adjacency matrix. So because it's the transpose, the edge from E to A of weight 4 comes across on the last element of the first row. And basically, this matrix is what we're going to deal with. And the algorithm that we're going to run is single source shortest path. And the four user-defined methods for shortest path are send message, you just send your current vertex distance to all of your neighbors. Process message, you take the message and add the edge value, which is a relaxation step in your shortest path. Reduce is once you have multiple edges, multiple messages, you just take the minimum of the two because you're taking the shortest path. And apply is basically, in this particular step, if you've actually found a shorter path than what you already have, then you need to update your current distance. So this is basically a Bellman-Ford algorithm for doing shortest paths. So we initialize this algorithm. Say we start, this is a single source. So we fix a source, in this case, vertex A. And we set its distance to 0. And what we do is send message, which basically creates a sparse vector. So it creates the vector 0, and everything else is empty after that. And then we do process message plus reduce to get an output vector. And this step is really what is doing the sparse matrix vector multiply. So let's just take one particular element, which is the second element for the output vector. So you take the second row and the vector, and we actually have to do a generalized reduction here. If you remember your matrix vector multiplies, you take the 1 on the row and the 0 on the vector, and then multiply the two. In this case, multiply is actually superseded by the process message function. So the process message function says add. So we add 1 plus 0, which is 1. And then if there are no other elements here to multiply, so we just write the output out. So that's 1. If there were any other elements, then we would basically take the minimum of the two. So once we do that, then there is the apply phase, where we basically take the current new distance, which is 1, and the previous vertex distance, which is infinity, and we take the minimum of the two, which is 1. So this is what happens, and this is completely opaque to the user. The user doesn't have to worry about it. You can think about it on what is shown on the right here. What we are really doing is taking this message 0 from the vertex A, passing it along its out edges to B, C, and D, and B, C, and D figure out that, oh, there's a shorter path from A through this edge than what I had already before, which was no path. So now they get to update their weights. So this process basically continues until the whole algorithm converges. So we did several optimizations to our code. One of the things that we have is to enable flexible graph partitioning, which means we can enable 1D, 2D, or block cyclic, or any other way to partition this matrix and lay it out in a distributed setting. This is pretty important because different algorithms can have different performance based on the graph partitioning. We have flexible data structures. We support compressed sparse row, doubly compressed sparse column, dense with bit vectors. All of these are useful for multiple contexts. And at the low level, we do perform a lot of compiler optimizations. We have enough software prefetchers and intrinsic support, and we do vectorization where we can. So what this enables us to do is outperform pretty much all of the, a lot of different graph frameworks. So compared to GraphLab and CombLab, Galois, and MapGraph, we are actually performing better. And this graph is averaged over 5 different algorithms, each running on 4 or 5 different data sets. The details are in our papers. You can look at it for more detailed information. So here you can see that we convincingly outperform GraphLab and CombLab. Galois is a task model. Of course, we are about 10% or so faster than Galois. But remember that we don't even have a multi-node version of Galois yet, because it's really hard to have a distributed task-based system running very efficiently. And MapGraph is a GPU-based framework, and we actually match the performance of that running on Xeon. And this is without even taking into account the time it takes to copy the data over from CPU to GPU and back. The other question is, well, it's faster than others, sure, but is it good enough? I mean, how much performance are we leaving on the table? So that's why what we did was take a few of these graph algorithms, optimize them by hand, do everything that we need to do to make sure that that particular algorithm is as fast as it possibly can. Now, once we did that, we saw that the performance is actually not that bad. We were within 1.2x of native performance on average, so within 20% of what you could actually get after you spent like several weeks sitting and optimizing each and every one of them by hand. Whereas you could write these programs in GraphMat in a couple of hours, or even less. Not just that, if we look at our scalability results, we did weak scaling, which means as we increase the number of nodes, we also increase the size of the graph. And we roughly kept about 128 million edges per node, and these were running on Graph 500 generated graphs. So compared to, say, something like GraphX running on, this is running on cloud, on an Amazon Elastic MapReduce instances. What we found that for both PageRank as well as shortest path, we are convincingly at least a couple of orders of magnitude faster than Spark and with GraphX. And this has kind of continued as we increase the scaling as well. So we've shown a pretty small, the beginning of the scaling graph. We're still continuing to evaluate the reasons for this performance gap and to see how things go once you scale to hundreds of nodes. Availability, GraphMat is available under open source and BSD license on GitHub. The QR code should basically take you to the GitHub website. Right now, we've open sourced a single node code. The distributed code should be coming soon. And we also have plans to integrate it with third-party data processing frameworks such as Spark. Right now, we are basically trying to have JNI wrappers so that you could intercept once you run something like PageRank. You can, instead of calling GraphX PageRank, you could just call GraphMat's PageRank, and everything should run fine. And we'll go for tighter and more interesting integration possibilities later. So in summary, we've tried to bridge the productivity performance gap for graph analytics. We are actually within 20% of native code performance, so we are not actually leaving a whole lot on the table. So you can be pretty sure that this is as good as it gets. And it's faster than pretty much all other graph analytics frameworks out there today. And you do not have to sacrifice any of your productivity advantages. You could still write Vertex programming. Integration with other frameworks is on the way, and the code is already available. I would like to acknowledge a lot of my parallel computing lab members who've helped develop GraphMat with their ideas and code contributions. Any questions? So on a machine with 64 gigabyte of RAM, we have run anything up to 500 million edges or so. I think, yeah, 1 billion maybe pushing it, but a little less than that we've definitely tried. Yes.
How long has GraphMat been released open source?
It's been a couple of months.
Not yet.
So we just released it soon, and we still, I mean, the distributed code is still not out yet. We've released a single node code, and the interface, the Vertex programming interface, is not expected to change at all, whether you're running single or distributed. So at least if you're planning to try it out on your algorithms, you should definitely try it out. And I mean, the idea is to integrate it with other frameworks. Our aim here is not to develop a separate competitor to GraphX or GraphLab. We want everybody to use this and make their frameworks better.